Page 8 of normal distribution. One last challenging problem where we're finding mean and standard deviation, and we know everything else. Circular metal tokens are used to operate a washing machine and a laundromat. The diameters of the tokens are normally distributed, and the only tokens with diameters between 1.94 and 2.06 will operate the machine. Find the mean and standard deviation of the distribution given that 2% of the tokens are too small and 3% are too large. Let's draw a little picture of that. 2% are too small and 3% are too large. Okay, so we are going to draw two normal distributions. One of them is going to be the x domain, and the other one is going to be the z domain. The x domain, we know that these numbers are 1.94 and 2.06, and we don't know the mean and the standard deviation, right? The z domain, we do know the mean and the standard deviation, 0 and 1 respectively, and we know the percentages are the same. What we need to calculate now, or we need to calculate the z values which correspond to 1.94 and 2.06. The way we do that, of course, is inverse norm because we have everything except for the zx's values. So let's turn on the calculator. Second, let's get out of this, quit, and then we're going to go second distribution, inverse norm, which is number 3. The area, we're going to put 0.02 first. It's the left area. So on the new calculator or on the old calculator, it's easy. Let's put 5 sig figs, negative 2.0537. Okay, and then we're going to find the number for this point here, which would be, let's see, we're not going to put in 0.03, we're going to put 1 minus 0.03 because we're going to convert the right side region into a left side region for the old calculator. If it's the new calculator, you could put 0.03 right. Of course, 1 minus 0.02 or 0.03 is 0.97, so you could just put in 0.97. The answer is 1.8808. Okay, now what we can do is we can take our formulas and relate these numbers, right? We're going to do z equals x minus mu divided by sigma. So that would be the z value, negative 2.0537 equals 1.94 minus mu divided by sigma. And then the other side is going to be 1.8808 equals 2.06 minus mu divided by sigma. And then we're going to rearrange them so that they're in the form blah 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 mu plus blah 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 sigma equals blah blah blah, one on top of each other. And then we're going to be able to use poly-SMLT to solve those. We don't even need to do the algebra. Okay, so put let's see, negative 2.0537 sigma equals 1.94 mu. So that would be, I'm sorry, 1.494 minus mu. So we're going to add the mu to both sides, and we'll end up with mu minus 2.0537 sigma equals 1.94. Of course, that's 1 mu. And then on this side, we'll do the same thing. We'll multiply both sides by sigma. 1.8808 sigma equals 2.06 minus mu. So that would be 1 mu plus 1.8808 sigma equals 2.06. Now we have these two equations with two unknowns. We can use poly-SMLT. And we're going to choose simultaneous equation solver, which is number 2. Equations 2, unknowns 2. Next. And now we're going to put in 1, 1, for the two mu's, right? We're going to put 1, 1. Then we're going to put these two numbers, these two coefficients, negative 2.0537, negative 2.0537, and then we're going to put 1.8808, and then we're going to put 1.94 and 2.06, 1.94 and 2.06. Solve. And the answers are 2.00. 3 sig figs would just be 2. And sigma is 0.0305. Yes, okay? And that is the correct answer. Last problem. Now this problem is actually given in the first section of the chapter, but I put it at the end because this is important for people who are going to use normal distribution in their IA, and it's kind of an interesting concept for people who aren't going to put it in their IA. It's something that we don't really think about when we draw the pictures of the normal distribution that we're constantly drawing. We don't really worry about how tall we make the normal distribution, right? That's something to think about. So like when you have a normal distribution, it looks like this, like we showed on previous pages, right? One of the most interesting points of the normal distribution is this center point, right? Because we can actually calculate it without actually graphing it. Look at when we put the mu value in this expression. If we put the mu value in for sigma, what happens to this function? Notice that we would end up with mu minus mu, which is 0. So this whole complex expression would just become one giant 0. And e to the 0, of course, is 1. So at the x value, mu, notice that the y value just becomes the coefficient. So the height of this peak is actually 1 over sigma square root of 2 pi. Now square root of 2 pi is just, some constant, never changes. But of course the sigma is changing depending on how wide the distribution is. So notice that like the wider the distribution is, the bigger the sigma is, the smaller this coefficient becomes, and the flatter the function becomes. So when the function is wide, it becomes flat. And all of this is in an effort to make sure that remember the area, the total area of this function has to be exactly 1.0, right? 100%. That's why when we find sections of it, we're finding the probability because we're finding proportions of the 1.0, right? So that's why this coefficient, becomes tall and short depending on how wide the distribution is, because we want to make sure that the distribution always 1. Okay. So what we're going to do now is we're going to draw different distributions as you might do if you're doing normal distributions in your IA. And when you draw different distributions with accuracy in your IA, you're going to want to pay attention to this height. Okay, so first thing we're going to do is we're going to take these three distributions, A, B, and C. Each has a different mu and sigma. Okay, and when we're going to figure out what is the peak height, the height at x equals mu for each one of these distributions. So basically we can do that by doing 1 over sigma square root of 2 pi. Okay, so let's do that. For sigma 5, sigma 2, and sigma 10, we'll do it for these 3 different points, 3 different distributions, and we'll write the height right there, and then we're going to graph each one by hand, just to kind of see proportionally what these 3 look like in comparison to each other. So the first one I'm going to do is sigma equals 5, so I'm going to do 1 divided by parentheses, and I'll do sigma 5, right? And then I'm going to multiply it times square root of 2 pi. 2 pi. Right arrow to get out of the square root, close the parentheses. So it's 0.0798. So this is the height for sigma equals 5. Let's do it for sigma equals 2. So sigma equals 2 would be 1 divided by parentheses 2 square root of 2 pi, right arrow, close parentheses, 0.199. Okay, last of all, we're going to do sigma equals 10. So that should be the shortest of the three because it's the widest. 10 square root 2 pi, right arrow, enter, 0.0399. 0.0399. Is that right? Yeah. Okay, so now let's graph these three. I mean, we're not going to graph it with a lot of precision, just, kind of precise. We're just going to try to show the relative heights of the three and the relative widths, okay? So first, let's try to graph this first one, which is 0.0798 high. It has its mean at 25, so its mean would be about there for A, okay? So let's do A in red. And the standard deviation is 5, and the height is 0.0798. So 0.0798, that's about 0.08, and 0.08 is about here. So it would be about there. This is the peak. And then the standard deviation is 5. So like 3 standard deviations out would be 15. So let's see, that would be about here, right? This would be about 15. So this would be the edge of the normal distribution. And then this would be the other edge of the normal distribution. Is that right? 15? Maybe it's a little bit less wide. Remember that 3 standard deviations out, the thing should be pretty much gone. So something like that. Okay, so there's my A normal distribution. Now let's do my blue B normal distribution. It's centered at mu equals 30, so it's centered right there. Its height is 0.199, which is basically 0.2, which is the top of the grid there. So that's the height, and it's very narrow, right? Because it has a standard deviation of 2, which means that you go 6 to the left or 6 to the right and the thing is already like gone. So it would be a super tall normal distribution. Something like that. Okay, so there's my blue B function. Very tall and narrow. Okay, so now let's do my green C distribution, which is centered at 21. And its height 0.0399, which is about 0.04. 0.04 would be right there. 0.04. So it would be there, and its standard deviation is 10. So you would go out about 30, and then the thing would be kind of disappearing. So like you go out about 30. Yeah. And then on the right side, it would go kind of like that. Okay, so there you have the 3 normal distributions graphed together on the same grid. And this is super important for IAs, because when you do your IA, you need to be careful, especially if you're superimposing 2 normal distributions on the same grid. Usually the normal distributions are not going to have the same sigma, so depending on that, you need to draw them accurately with, varying heights. The height should not always be the same. All right, so that's why we talked in such depth about graphing the normal distributions.